our workshop for the PROTECT project. I would say good morning if you were in the UK, but most of you are not. So I'll say good afternoon to those in Turkey. And I guess there are some people in other places, so it's good day to everyone. My name's Peter Rickaby. I work at the UK Centre for Moisture and Buildings at UCL, so I'm part of the team for this project, and I'll be just chairing the session today. Would you like to click on one, Negin? Here are our project sponsors. Principally, the work on this project is funded by British Council's Newton Fund, Institutional Links, and TÜBİTAK in Turkey. And then below that, you see the participants. We have, I'll just move that out of the way. We have UCL in London, Middle East Technical University in Ankara, Sustainable Traditional Buildings Alliance in London, UK CMB at UCL, and Saika Architecture in Turkey. If I've left you out, I apologize. However, that's the list I've got. And so this is great, a big collaborative effort between several groups to try to understand the energy performance of traditional dwellings. Move us on one, please, Negin. So our objectives of our project overall are to investigate the energy performance of a set of Turkish traditional dwelling types in different climate zones, different areas, and to agree appropriate retrofit objectives for each type and explore them, to assess and identify the most cost-effective options for improving energy performance in those buildings, which we know, of course, are very both technically and socially sensitive, to quantify those improvements if we can by modeling, and that's the focus really of what we want to talk about today, and to identify ways in which we can promote appropriate options to target communities in Turkey, to build our research and engagement between ourselves, between the various groups involved in this project and surrounding it, so that we can develop deeper and better academic collaboration and support for policy. And then one more, I think, yes. And then to provide some knowledge exchange within this broader research community that we've created, with a review to some capacity building and so on, and some dialogue. So this is one of our capacity building workshops in many ways. The program for today is shown on this slide. We're going to hear first from Negin Jahed, who's working with us at METU, and is going to give us an overview of progress of the project. And then we have 4 distinguished speakers, not quite in the order that it shows on this slide. The first, after our session break, the first speaker will be Zeynep, but then we'll go on. Oh, somebody's changed it and put it right. Yeah, okay, so we've got it pretty much right now, and Valentina will come last. Okay. Somebody must have changed that on me. Okay, thank you. So that's how we're going to proceed. If you are participating, it would be good if you could keep your microphone muted so that we don't get background noise. I think we're relaxed about whether you keep your camera on or not. If you wish to ask questions, then please put questions in the chat, and one of us will collate them, and we'll talk about those we'll deal with those during the discussion. Otherwise, I hope you enjoy the session. We've got nearly 4 hours of good thinking and good presentations, I think. So I'm now going to hand over to Negin, who's going to tell you where we've got to so far with this project. Negin, the screen is yours.
Thank you, Peter, and hello everyone. Thanks for all our attendees for today. My name is Negin. I'm an architect and at the same time a PhD candidate in Conservation of Cultural Heritage Program in Midwest Technical University, and jointly supervised between METU, UCL, and UK CMB. Through this presentation, I will talk about the project progress, mainly the progress of input data collection for our base energy simulation. I will begin with a brief overview on the work streams and the progress so far accordingly. Then we will have a look at how we harmonize energy efficiency, conservation, and user comfort, and how our team is a structured multidisciplinary team with a well-defined energy retrofitting process for traditional dwellings. Finally, the presentation will be completed with a quick look at our process on ongoing baseline energy simulation. And at the end, we will have 10 minutes for your questions and discussion part. Yes, as you can see in the table and also the diagram, the project is organized in 4 main work streams divided into various tasks. As you can see, the first year of the project attributed to the first and second work streams will be used for data collection via field surveys, energy performance modeling to provide a robust and quantified problem definition. And the second year will be used to establish protocols and develop retrofit measures to enhance energy efficiency of the identified cases. At the moment, we are very close to complete the second work stream through simulating our base energy simulation model and quantify the performance gap between the modeled and monitored data. Yes, when it comes to Turkey climatic classification, Turkey is mainly situated in a temperate Mediterranean climatic and geographical zone, but there is significant differences in climatic conditions. As you see in the map, the Black Sea region in the north is mild and generally rainy throughout the year, with the temperature neither very low and in winter and no very high in summer. The southern and western coastlines have a typical Mediterranean climate with mild winters and hot, dry summers. And the interior parts of Anatolia and eastern Anatolia are marked by cold and snowy winters and hot, dry summers. For this project, the selection of the representative cities is based on climate classification of Turkish standard for thermal insulation requirements in buildings called TS 8025 as the mandatory document that determines the thermal properties of envelope materials. Beginning from the eastern part through the map, our representative cities are Bitlis, Hatay, Güdül in Ankara, Safranbolu, and Milas. And we expect that the results of the project from these representative cities can be generalized to the similar geographical regions. Yes, the most important part of our presentation, how we harmonize these 3 strong domains with each other. As you know, the heritage buildings, despite their environmental credentials, environmental credentials in terms of passive heating and cooling, lighting, ventilation, and good orientation. However, due to their age, lack of maintenance, and previous damage, mainly may demonstrate poor energy performance that makes them more vulnerable to the consequences of changing climate. However, on both national and international levels, buildings with heritage values are often excluded from policies and regulatory frameworks, unfortunately. And in the case of Turkey, traditional housing stock is estimated to comprise more than 70% of the registered heritage building stock, which is a considerable amount. On the other hand, we can say that energy retrofits are not seen as a threat to the conservation anymore, but as a measure to help with the protection of heritage and ensuring healthy environments for a longer lifetime. Certainly, for the heritage buildings, the main focus may not be the maximization of energy consumption, but should always be the search for an optimal intervention respecting the constraints of the heritage values and user expectations. This project has been structured in 3 levels, as you can see: energy efficiency, conservation, and use. When it comes to the energy efficiency part, the main factors affecting the energy efficiency are climatic conditions, environmental impact, fabric thermal assessment, and energy systems. To assess the fabric thermal performance, we will use U-value measurements, IR thermography, air tightness measurements, and environmental monitoring using temperature and relative humidity sensors. And for the environmental impact assessment, regional risk assessments and CFD infiltration analysis will be conducted. Finally, for assessing the pre-retrofit and post-retrofit energy performance of the building performance simulation will be run at different stages of the project and will compare the performance gap between the modeled and monitored data. At the conservation site, the most particularly the most important factors that should be considered in this part are condition, integrity, and authenticity. For this, it is essential to have an in-depth knowledge on the building material and construction and its architectural characteristics. After that, for assessment, structural and material condition, change assessment, and heritage value assessment. And all these assessments will be consulted with conservation experts while choosing the most feasible retrofit scenarios. At the use part, we will try to have a wider perspective of user needs and user expectations through questionnaires. And at the end, all these levels will be harmonized to meet the main aim of our project, which is the impact assessment of developed retrofit solutions. The project, through its pathway on developing energy retrofitting solutions for traditional dwellings of Turkey, brings together a highly interdisciplinary and integrated research team with a wide range of disciplines from both UK and Turkey. It builds upon Turkey team's expertise in architectural heritage conservation, site management, conservation policy, and community engagement. And at the UK team's expertise in energy efficient retrofit, monitoring climate-induced hazards and moisture damage. PROT3CT energy performance assessments for traditional dwellings follows three main steps in the frame of defined work streams. The first step is collecting input parameters to be able to run baseline energy simulation for design occupancy profile. The second step is the analysis of real energy use patterns extracted from utility bills and evaluation of performance gap. And at the last step, an energy retrofit model will be developed based on recommended scenarios with respect to heritage values, energy efficiency, comfort, and reduced operating costs. Lastly, the unintended consequences of retrofit, moisture risk, and different occupancy scenarios will be assessed in the frame of the retrofit impact assessment. Today, we are at the first step of the energy performance assessment, which is collecting input parameters for our case building in Milas, located in the temperate Mediterranean climate zone in the western of Turkey. Our building in Milas is a 19th century house, has been recently restored. It is built in Hemish construction system. In Hemish construction system, we have three main structural parts of stone and brick masonry base, timber frame brick infill upper floor, and timber roof. The foundation, which is built with rubble stones, extends, in our case, almost 1 meter up to the ground floor level. The ground floor walls are made of stone and brick masonry. The exterior wall thickness is around 60 centimeters. The timber skeleton of the upper floor is constructed by using vertical and horizontal elements and supported by diagonal braces. Brick is used as infill material for the intervals between these timber elements in the upper floor. In the timber frame upper floors, two of the exterior walls, as you can see in the plan, one of them serves as a service wall and other embraces chimney, is built in masonry system, and the masonry system continues to the upper floor in these walls. In addition to the use of brick as infill material, another use technique in the house is the Buda technique that you can see in the projection part in the front facade. In this technique, both the interior and exterior surface of the walls are covered with timber lath and then plastered over. Milas houses are generally 2-story and rarely 3-story high buildings. Our building is a 2-story building with inner hall plan type called sofa, which is a common space, and rooms are gathered around this space. The function of sofa could be gathering and living space, dining space, and circulation area. As you can see, the main entrance of the house is from the street. It has a courtyard at the back, and the entrance part from the courtyard is through a transition space which is built in later periods. The access to the upper floor is from a timber staircase embedded in a brick masonry wall. Rooms are seen both in first floor and ground floor. There are 3 rooms at upper floor, which used as bedrooms. You can see they are very rich in their architectural characteristics and elements, sailing wooden ornaments and chimneys, fireplaces. When come to the monitoring hydrothermal performance of the building, 4 temperature and relative humidity data loggers have been mounted in the building, 1 indoor and 1 outdoor sensor, and 2 for surface temperature measurements. Information about energy systems and energy use patterns have been collected through in situ expert observations and social questionnaire asked for residents. Through these observations and respondents' complaints about comfort problems, we see that there's existing moisture problems result from the rising damp and roof leakage. According to the residents, due to the uninsulated fenestration and also roof part, there is also considerable infiltration rates and consequently heat loss in winter times. Yes, the other important input parameter needed to be inserted to our base model simulation is thermal performance values of different materials through the fabric. However, due to the difficult circumstance of the pandemic, we couldn't apply in situ measurements, but we are planning to do it. And so in this stage, we collected the U values from literature on similar structures and materials. We are planning to collect the precise data and heat losses and moisture detection through the fabric using infrared thermography testing, air tightness measurements, and also U value testings. Right now, we are at the stage of creating our base energy performance model. To be able to edit energy plus input files, we successfully created the building's Open Studio 3D geometry according to all the measured and collected data and information by now. You can see the model and its boundary conditions and different space types. We define our space types according to common characteristics like internal loads, schedules, occupancy patterns, infiltration, and construction. And since the usage patterns of ground floor and upper floor spaces vary in different seasons, accordingly, we keep all these 10 space types as separate space types. However, in the case of rooms with the same characteristics at the same floor, we assign 1 space type to each. In terms of thermal zones, we define the thermal zone based on as a volume that is served by a heating system. So we define 5 main thermal zones as unconditioned spaces comprising sub-basement and attic part, and service spaces like kitchen, bathrooms, and the annex bathroom, corridor, living rooms, and bedrooms. And our further steps to complete our base model are scheduling occupancy profile scenarios, internal loads, construction states and materials, and also safety infiltration analysis. Thank you very much. We have a couple of minutes to receive your questions and have a discussion part right now. Thank you.
There's one point being made in the chat about some of the problems you mentioned, Negin, are mostly caused by unwanted interventions and changes in the environment, changes of water table due to big construction projects and so on. I don't know whether you want to respond to that. Otherwise, we've got about 10 minutes before we break, so we can either have some questions or we can let Negin off the hook and have a longer break. It's entirely up to you all. So happy to invite questions now. Question from Hector. Could you please clarify where you have located the data loggers? In one of the pictures, one of them was next to a window. Is this correct? That's from our colleague Hector Altamirano in UCL.
Let me see again, share my screen. Yes. As you can see, we have one outer and one, oh, sorry. Oh,
That
okay.
one.
One outer surface temperature and one inner surface temperature. You can see here one of them is mounted on our front facade, and the other one, inner surface temperature, is right at the back part of this sensor from the indoor part. And here is the picture next to the front facade one. And we have one outdoor data logger mounted in the back courtyard at the back of the building, and the other one is in the sofa part. Let me see from the plan. Yes, here in the first floor part, mounted on the one of the interior walls in the sofa here. The question was about the locations. Yes, or?
Well, I think Hector was interested in, well, he said thanks. You seem to have given him a good answer. I'm assuming you put them near the window because it was easiest to get them there and they were out of reach of people outside. But I also wondered whether you were trying to measure the temperature inside and outside simultaneously, as it were.
Yes.
Okay. We have another question from Hassan. Hello, everyone. I have a terminological question. What is the correct terminology for improving building physics characteristics of a building with installed implementations? Retrofit or deep renovation? There is an incomprehensibility in the literature on this topic. I'm sympathetic to that question because people also talk about refurbishment. So we have lots of words for what people often treat as the same thing. Negin, do you want to give a view on that?
Peter, I can't see the questions right
Okay.
now. I'm searching for where you read them.
It's in the Q&A. I'll read it again. What is the correct terminology for improving building physics characteristics of a building with installed implementations? Retrofit or deep renovation? There is incomprehensibility in the literature on this topic.
Yes, actually, the retrofit and also the refurbishment are used exchangely, but it's not true. Retrofit has a mainly general definition, I think, from refurbishment. So I think, yes, Peter, you can define it correctly.
Yes, well, I tried to use retrofit mostly to mean doing things to the building to improve its performance after it's been built, later in its life. I think that you can use other words, deep renovation. Renovation to me implies doing more than just energy measures. It implies making the building comfortable again and habitable again and secure and dry and everything else again. So in many ways, renovation is a better method. But retrofit is certainly in the UK, the term we apply to installing energy measures to improve energy performance. I've got a question from Denise. Did you detect interventions to the buildings? I assume he means things that have been done previously to the buildings we've looked at. Do you want to do with that one as well, Negin?
The problems are mostly caused by unwanted interventions and changes in the environment. Change of water table due to big construction projects. So it was not a question, I think. Sorry.
Okay. I think what Dennis is asking is had things already been done to the buildings? And I think the answer there is mostly no, isn't it? I mean, obviously they've adapted a little to modern life, but they haven't been significantly changed. Another question from Hector. How are you assessing comfort problems? What kind of questions are you asking residents? I feel as though we ought to ask Yasmin to answer that question, if she will, because Yasmin's been talking to the residents. Are you there, Yas? She's not answering.
Yasemin hocam.
She must have got distracted. Okay. Well, let's go back to the question. We are talking to the residents and we are asking them questions. We have a big questionnaire which covers lots of things, including how they use the building and how comfortable they feel and where they are in the building at different times of year. So we do have some information about that. I've got another one from Nigel Blades. He says, would it be useful to have more indoor temperature and relative humidity sensors since you're going to simulate several zones inside the building? I think the answer to that is yes. We had some difficulties in gaining access because of pandemic restrictions and so on. So the time and scope for installing sensors was quite limited, but we have managed to get some sensors, as Negin explained, into the Milos building, and we are putting sensors into one of the other buildings. I think you can never have too many sensors, but we are where we are. We've got a finite number. It would be great to do more, definitely. I have a question from Hassan, except that I can't read it. I just know. Denise has come back. What I mean is most of these problems will be solved if unwanted interventions are removed, probably. Did we assess that? So is it a good idea, in other words, to remove bad interventions that have been made previously in order to restore the building to its original condition in some way? And I think we would probably all agree with that. We haven't encountered that particular issue yet in this project. We haven't felt the need to look at recent interventions and remove them quite yet. And I've got one from Dilara. Is a permanent user structure a priority for retrofit applications? Can idle structures, I assume by that is meant unoccupied, be pilot examples for retrofit studies under refunctioning applications? So can we cope with buildings that are unoccupied, I think is, and does that help us to understand them? In fact, the Milas building is substantially unoccupied for the last few months, so we're having to cope with that ourselves. Okay, that's all the questions I've got for the moment. It's now 10:33, so we're a few minutes early for our break. But what I suggest we do is we start again as we plan to at 10:45 and have an 8-minute break or so, 12-minute break, and then we'll continue into session 2. So if you're happy with that, we'll return in a few minutes' time. Okay. Right, it's 1:45 in Turkey and 10:45 in London. So I think we should now start on our second session. We have four 5 actually distinguished speakers for 4 presentations over the next couple of hours. I'd like first to introduce Zeynep, Durmus, Arsan, who's going to talk to us about case studies or cases of dynamic performance modeling of traditional buildings in Turkey. Zeynep comes from Izmir Institute of Technology. Zeynep, it's over to you.
Thank you. I will start sharing my screen.
Yeah, we've got it.
So thank you. Thank you for your invitation. Thank you for the organization. I'm proud to present this slides today in the Women's Day. So I would like to first start with celebrate Women's Day, especially for Turkey. I'm an architect in the Department of Architecture in Izmir Institute of Technology. And today I will present our first research group, which is Ipek in our university. Then I will explain a little bit about factors affecting traditional dwellings in Turkey. And I will enter to the core topic, what is dynamic performance modeling of a traditional dwellings. And I will present 7 cases, which is not well known. Some of them are not published, so I hope you will enjoy. So most of the cases that I will present today are the research conducted in our research group. So it is Ipek, composed of architects, architecture restoration specialists, energy engineers. And among all these research interests, historic buildings and energy efficient retrofitting of them are one of the prominent areas. On the historic buildings, we've mostly focus on these research interests: building performance modeling, performance monitoring, thermal comfort issues in historic dwellings, buildings, and impact of climate change. The studies focus on different types of historic buildings, such as mosques, mostly in the Aegean region, old library, and of course, traditional dwellings. Now, we will focus on the dwelling culture of Anatolia and see first the factors affecting traditional dwelling practice in Anatolia. Turkey is located on the very intersection of old continents, such as Asia, Europe, and Africa. This is the main source of its unique cultural richness, and it is one of the oldest permanently settled regions of the world. And especially, I would like to focus on the dictionary meaning of Anatolia. Anatolia is related to mother, and also it is related to east in terms of rising sun. So it has specific meaning. In terms of geography, the altitudes rise from west to east, and you can see here the highest mountain, which is famous mountain, Ararat Mountain, over 5,000 meters. And this inhomogeneous land formations are also cause to diversification of dwelling culture. Depending on the diversity in its geography, the country show climatic variations, such as semi-arid areas on the middle, Mediterranean on the west and south, subtropical and oceanic on the north, some Mediterranean continental and on the middle and east, and some subarctic and continental climates on the northeast. So these climatic variations assist the establishment of great diversity among traditional dwellings. We have also high earthquakes, especially we have two main continental fault zones, and the ground quality and earthquake resistance also affect the evolution of form, material use, and dwelling culture also. Here I presented a timeline for Anatolian land. As presented by this timeline, Anatolia has witnessed many civilizations over 10,000 of years. Each civilization with its unique character has left distinctive marks on the overall cultural repertoire. And as a result, the most remarkable feature of cultural heritage in Anatolia can be summed up as the intensity and variety within a multi-layered structure. This multi-layered structure is also reflected into dwelling culture that varies in design with changing geography, climate, and available local materials. So far, it is one of the most characteristic architectural elements of Turkish houses. It's a common place between rooms, and actually it's a kind of hall where the circulation is conducted. Beyond the circulation, it is sofa is also seating, working, and assembly area. And the dwelling typology can be grouped into four in terms of its availability. I mean, sofa's availability and location in the dwelling. We can tell central sofa houses or dwellings, inner sofa, outer sofa, and without sofa. So let's face with the core subject of this workshop. If we ask what is dynamic performance modeling of a traditional dwelling, it is a digital model that is capable of replicating dynamic performance of traditional dwelling in response to external and internal influences on time scale of 1 hour or less. We need digital models giving reliable results. In order to reach a successful model, we firstly use software packages whose reliability approved by best test, building energy simulation testing methodology. Dynamic modeling of traditional buildings is different from architectural modeling. It is an unpredictable process. There's a need for correct data input. Firstly, the building geometry should be entered, yet modeling deals with a certain degree of abstraction. It's not a detailed representation of all geometry and processes in the building. So when we model a traditional dwelling, we may lose too many details of dwelling. This is one of the obstacles we faced. Secondly, we are dealing with unstandardized materials. We mostly don't have information about thermal qualities of materials. Sometimes we even don't know the exact materials inside the building component. This makes modeling more complicated. The rest requires similar data entry process, location of dwelling, climate data, vegetation such as tree and bushes, and their obstacles, user profile and habits, usage operation time schedule, lighting and air conditioning systems information are entered as in modern buildings modeling. If we don't know material characteristics, for example, a traditional wall, how to find its thermal properties? There are several ways to do predictions. One way, and maybe the first way, to conduct a literature review, to collect basic info about similar materials. Secondly, we can use the material library of software to do some resemblances with the particular materials in the dwelling. We can conduct the material mineralogy testing such as XRD, XRF, in a comprehensive laboratory to find such as stone, brick, or mortar type and mixture. If we can obtain a sample of the material, thermal conductivity, density, and specific heat can be measured in the laboratory conditions because these parameters can mostly be enough to define the material in a dynamic software. And lastly, on-site U value measurement campaign can be organized in a proper cold day to obtain thermal conductivity value of a building component. This is the valid study if we don't know the inner composition of the building component. The other step to reach a successful model is to conduct monitoring campaign for thermohygrometric parameters and air types measurements. At least 1 year monitoring is recommended for inside and outside conditions of the dwelling. Therefore, collection of local meteorological data becomes essential. The digital model of dwelling needs to be calibrated by using measurement data with respect to ASHRAE for guideline 14. This guideline defines error ratios based on comparison of monitored hourly or monthly average data with simulated one. The error ratios introduce two-dimensionless error indicators, mean bias error and coefficient of variation of the root mean squared error. MBE measures how close the data predicted by the model corresponds to the metered data, and the latter is referred to a measure of variability or how much spread exists in the data. Calibration also requires an endless iteration process until the model reaches the minimal error ratios, and its parameters can be energy consumption, air temperature, and relative humidity. Let's start with summarizing cases from Turkey. I will present 7 case studies related to dynamic performance modeling. For their location, 3 of them is located in Izmir, 2 Muğla, 1 Konya, and 1 in Şanlıurfa. 6 of the cases are the thesis, 3 masters and 3 PhDs conducted in Izmir Institute of Technology. We have 1 neighborhood scale study, and the rest is single dwellings. One of the dwellings represents the house type with its exterior sofa, and the rest is without sofa. And 3 case studies are conducted in adobe buildings, and the rest are on stone timber mixture. Lastly, dwellings represent 2 climate zones, such as Mediterranean and continental. The first case is the master thesis with the name of Effect of Natural Wall Materials on Energy Consumption in Continental and Mediterranean climates. Here we see 2 adobe dwellings from southwest of Turkey and central Anatolia, representing Mediterranean and continental climates. The general aim is to understand energy efficiency of dwelling constructed with natural building materials in different climates. This was the comprehensive optimization study on searching relationship between natural wall materials and energy consumption. Here you see the research questions of the study. What is the most suitable natural material according to climate? Is it possible to make combinations of materials on different wall directions of the building? In which material combination is the energy load less? So 2 houses were monitored in 2017 for 45 days, both externally and internally, to measure temperature and relative humidity in 10 minutes, in every 10 minutes. Design builder models are created and calibrated based on hourly internal temperatures. Here you see totally 20 base wall options composed of adobe, vertical hollow brick, limestone, hempcrete, and straw bale with 30 and 50 centimeter wall thicknesses and without and with flex thermal insulation material. They are tested with different combinations of direction and climate. The wall option 1, 1st and 6th are referred to as Muğla and Konya case buildings, while other wall options are referred to as base scenario. The thermal properties of materials are selected from literature review. The optimization tool of Design Builder is used for simulations, and 8,000 simulations per each location is conducted. In conclusion, straw bale enables the minimal annual energy consumption, both for Mediterranean and continental climates, while ADAP shows better energy performance in summer period of continental climate. Besides, the energy consumption for cooling in Mediterranean climate is around 10 times higher than of continental one for whatever material is tested. The second case is also conducted in the same house in Konya, namely impact of high thermal mass for future energy consumption. This study examines thermal mass quality of building envelope as passive preventive phenomena for future energy consumption. It questions how much and what type of thermal mass is required for decreasing energy consumption according to future climate change. Summer energy performance of ADAP house in a continental climate is studied in terms of thermal mass characteristics by using dynamic software. Measured and predicted microclimate data for 2017 and 50s are used to compare passive impact of wall material choices without nighttime ventilation. This study includes the following methodological steps. Firstly, measurement of climate data, that is monitoring process for generating 2017 and 50s microclimate data. Secondly, modeling, simulating, and then calibrating the base building, case building according to monitoring results. Thirdly, creation of thermal mass scenarios based on wall materials. And fourthly, comparison of summer energy consumption values. In conclusion, we don't utilize nighttime. If we don't utilize nighttime ventilation, it is deduced that thermal conductivity will still have higher impact than thermal mass on energy consumption. This study reveals that thermal mass with lower density and thinner materials show higher energy performance for summers. The third case, thermal retrofitting on traditional buildings with exterior hall or sofa, is from the southwest of Anatolia, as you see here. This is the PhD thesis aiming to examine the thermal behavior of traditional houses with exterior halls and to determine enhancement potentials of possible thermal interventions which will not cause any value loss. The method of the study consists of on-site thermal measurements and transient thermal analysis of case studies utilizing software Design Builder. Case study buildings were selected from both urban and rural settlements of Muğla city in order to detect possible effects of prevailing microclimates. Case dwellings were monitored for 1 year, both externally and internally, to measure temperature and relative humidity in every 10 minutes. Both design models are created and calibrated based on hourly internal temperatures. The results show that application of thermal insulation into roofs and floors between stories, air tightness, operation, control for windows, shutters, addition of secondary glazing to window frames, and creating circulation corridors connecting rooms provide significant improvements in the thermal performance. According to simulation analysis, it was determined that these interventions would save 38% in total energy use in urban city center and nearly 50% in rural sub-settlement. This improvement percentage can even be increased to more than 80 when the ground source heat pump integration is implemented. Now we start cases from Izmir in Western Anatolia. Fourth case is again the PhD study, namely comparison of architectural design parameters in traditional buildings in terms of their energy performance for future housing design. The purpose of the study is to examine the architectural design strategies of vernacular dwellings in terms of energy efficiency for future designs of residential building in hot, humid climate of Izmir. It's aimed to find out the least energy consumption 19th century Izmir house type and design parameters impact on energy consumption. So for the method, on-site measurements are made at 2 buildings chosen at the base cases from Izmir city center. Then these buildings are modeled and simulated with design builder software. After the calibration, variant typologies of 19th century Izmir houses, differentiating according to architectural design parameters such as internal space arrangement, building form, facade organization, and settlement pattern and orientation will be was modeled and simulated. Such parameters as location of hall, plan type, utilization and existence of basement, occupancy of the roof and existence of the oriel were determined according to the basic characteristics of 19th century Izmir houses. Among the results, location of the hall, plan type, existence of the basement are found the most effective parameters on the building energy performance. The case 5 is about energy efficient retrofitting of a refunctioned historic dwelling that is Basmane district center in the city center of Izmir. Design builder software was used to determine the impacts of energy efficient retrofits. Building energy simulation model was calibrated by comparing the results, the measured and simulated indoor temperature and energy consumption. Long list of retrofit options for historic building is prepared as you see in the left chart. The retrofit options are evaluated according to six assessment criteria such as energy saving, economic heritage values, durability, moisture, and indoor environment. These are defined by the European standard 16883, Conservation of Cultural Heritage Guidelines for Improving the Energy Performance of Historic Buildings. According to risk levels here, colored from red with the most risky to dark green with high benefit, retrofits were evaluated with the local facts and gathered into 3 packages. As you see, 3 packages. The aim of the first package is to meet the energy targets without altering the building appearance and damaging the heritage values. Package 2, more interventions are included, and package 3 was intentionally grouped with inappropriate retrofits in order to determine the maximum possible saving. The results show that the energy saving of more than 34% can be obtained without damaging the heritage values with the package 1. Case 6 is the master thesis presenting a pilot study conducted at neighborhood scale consisting of 22 early Republican and contemporary residential buildings in the historic urban fabric of Izmir. This study underlines that in large-scale rehabilitation projects in urban areas, the study should start with how to decide solutions. We should at least guess which buildings providing the most energy saving, and the decision should be done in a short time. Therefore, the study was utilized building performance simulation model and conducted a numerical analysis to determine the most related design parameters affecting annual energy consumption. All case buildings were classified into 3 main groups as Group 1 officially registered, Group 2 historic yet unregistered, and Group 3 contemporary buildings. Retrofit solutions are determined considering 5 leveled assessment scale of European standard 16883. Here you can see the impact assessment of retrofit solutions for Group 2 buildings. Totally 17 solutions were determined and 15 of them are selected. 2 retrofit packages with different risk category was decided. As a result, this study provided information regarding different energy efficient retrofitting approaches for different building categorizations. For example, 3 buildings here representing each building group is determined initially be retrofitted, and their energy savings ratios are given. This study indicated the evidence for the possibility of decreasing energy consumption on a neighborhood scale without extensive data collection and in-depth energy audits. And lastly, the last case, Harran House, is from the southeastern Anatolia, Şanlıurfa. The climate of Harran is very hot at daytime and very cold at night. So the dwellings are built with adobe, brick and stone around the large courtyard. This is a PhD study, namely investigation of the effects of different roof geometries on building thermal behavior. So the objective is to investigate the effect of this conical roof geometry on indoor air temperature by comparing with flat roofs to ascertain which of these 2 roof geometries is more energy efficient during summer months. CFD simulations are conducted to analyze forced convection, heat transfer coefficients, and cross ventilation performance for these 2 roof types. Because of its conical shape, the dome has always shadowed area, causing pressure difference and air velocity and removal of heat by convection. As we see on the right, there's a hole on top of the roof and side of the dome, and it's closed in winters. Open in summer and closed in winters. As we see on the ventilation diagram here, at the left in daytime, there is a vertical cross ventilation through side window and top hole. And hot air rises and extracted through the top hole. In the result, it's found that for a typical summer day, the indoor air temperature of Harran House is lower than a flat-roofed building. Cross ventilation flow rate for the house with conical roof is found to be around 10% higher than that of the flat one. And the conical roof transfers around 30% less heat to interior side. In other words, more heat absorption in the flat roof. So this was my last slide, and thank you for your patience and attention.
Thank you. That was fascinating. I'm struck by how close the studies you've presented are to the study we're doing ourselves with Protect. And I think there's scope for lots of rich dialogue between you and your colleagues and our team. However, I want to just postpone the questions now because we're a little behind time. Yes. So if we could take the questions in the discussion at the end of the presentations, that would be great, if you're happy with that. And I'd like to move on now to and bring us back to Middle East Technical University and hand over to Ipek, Gursel, Dino, and Shala, Meral, Akgul, who are going to talk to us about residential building performance under climate change. So, Ipek, over to you.
Thank you, Peter. First, let me share my screen. Okay. Is it on full screen now?
We've got your second screen with the
Yeah.
2 slides showing.
Okay. Then I'll try something else. It's always very difficult to present with 2 separate screens. So okay, does it work now?
That's good, yes.
Excellent. So, Peter, thank you very much. Like Zeynep Hoca, it's with great pleasure we are sharing this platform with so many great women scientists. So it's a very, very important day to be presenting today. Our presentation today is going to be with Cagla Meral Akgul. She is also here with us amongst the others. Other people. First, I'll just give a brief introduction about our research in general. So we have been collaborating with Cagla for a long time now. This collaboration takes place between the Department of Architecture and the Department of Civil Engineering. And our research focuses on building energy performance, sustainability, climate change adaptation and mitigation in the built environment. And to do so, we adopt a methodology based on computational methods and tools, including modeling and simulation, just like Zeynep Hoca was explaining a minute ago, data analytics, and computational data analytics, computer vision, and machine learning. And today, what we are going to talk about is it's based on our previous publication on climate change impact on residential buildings and the ways in which buildings perform differently under these changing climatic conditions. Okay. So some general information is between this interrelationship between climate change and buildings is that the built environment is a high priority area for climate change because there's a complex and a very sensitive balance between these two. And according to the International Energy Agency, the greenhouse emissions and the total energy consumption of the built environment constitute 30% of the total global anthropogenic emissions. And to be able to keep global warming only below 2 degrees, CO2 emissions need to be reduced by 77% by 2050. This is quite an ambitious target that we are targeting, we are aiming at the moment by architects and engineers alike. The environmental consequences of climate change, as we all know, are great. Global warming, particularly, is expecting to change building energy use from heating towards cooling because of the increased temperatures. And these will have different consequences in the resulting CO2 emissions based on the climate that we are analyzing. Also, HVAC system inefficiency and malfunction due to these changing operating conditions is something that we have to consider in the future. We are feeling the impact of extreme weather at the moment. A couple of weeks ago in Texas, the grid electricity completely went out, and many similar problems arise for overheating during summer, especially in Europe lately. There are also some important comfort and health implications of climate change and global warming. extreme heat waves are expected to last longer and become stronger and more frequent. And overheating, occupant overheating over lengthy periods poses serious threats to the comfort and health of occupants. And occupants of residential spaces are important for us because they are most exposed to heat during the day. And they are typically those that cannot effectively take adaptive measures to keep cool, such as the elderly, babies, younger children, those that are living alone, sick or bedbound. So there is a very high level of vulnerability that comes with global warming. And domestic energy poverty may limit the reach to effective means of cooling. This is a big problem. So transforming towards a reduced energy future is not very easy because of some financial constraints. When we come to Turkey, climate change, Turkey is going to be influenced by climate change a lot because it's located in the Mediterranean basin, and the robust and consistent climate change process is expected in the future. So we project increasing temperatures, a pronounced decrease in precipitation, which I'm sure we are all experiencing this together with the participants from Turkey. Rainfall has reduced a lot during the year, and an increase in both the frequency and magnitude of heat waves, change in diurnal temperatures and winter precipitation, scarcity of fresh water, and problems regarding poor air quality, droughts, decreasing crop yields, and an increased risk of vegetation is awaiting, especially in the Mediterranean basin. Residential buildings, as I mentioned before, are expected to be influenced by climate change to a great degree. And we have to place additional emphasis on residential buildings. Because we have a very high, the population in Turkey reached 82 million and counting, and the growth rate is quite high. And there is an increasing demand for indoor occupant comforts and a global trend towards larger buildings occupied by smaller families. This means that the energy demand and the carbon dioxide emissions or global warming potential per person due to residential buildings is increasing constantly. And so from here on, I'm going to base all the facts and all the arguments on a publication that we co-authored with Cagla, Meral, Akgul, and it focuses on a detailed impact analysis that evaluates the consequences of climate change on residential buildings in Turkey. Similar to Zeynep Hoca, a simulation-based assessment was made for a typical residential building by TOKİ. TOKİ is, it's very difficult to explain what TOKİ is. It is a mix of social housing and different types of construction activities targeting different building functions. But a very typical building design was analyzed for 4 representative cities that characterize distinct climatic conditions. And we, in Turkey, we very typically use TS 825 thermal installation requirements in buildings. So it's an adaptation of ISO 9164 thermal installation calculation of space heating requirements for residential buildings, and also the European standards EN 832, and it's an adaptation to the Turkish context. And it's very important to highlight that TS 825 follows a heating dominant approach, which means that these categorizations are based on heating degree days. But given that climate change is going to shift the balance between in temperatures, it fails to capture the complexities that come with climate change and global warming, and it completely misses out on building cooling, and for this reason it is very widely being criticized. And it neglects cooling loads and the heat store capacity also, as a separate item, the heat store capacity of buildings. Nevertheless, this is the standard that we are using in Turkey at the moment, and many decisions regarding the building envelope material selection need to be based upon TS 825, and this is what we did for our building. For the envelope materials, we followed the U values mandated by the standard. And so this is the building. To the right hand side, you can see an isometric view of the building and also the standard floor plans. A very typical building that you might come across in Turkey, with 3 bedrooms, 1 living room and 1 kitchen and some service zones, including the corridor, storage and bathrooms. And to be able to generalize, because the bedrooms are towards the north, east and west, it's very difficult to generalize based on different room types. So we had to take multiple simulations by changing the orientation of building by multiples of 45. And this resulted in 192, if I'm not mistaken, 192 simulations in the end. So we also considered a different number, 3 different cooling scenarios. As I said, cooling is going to be the major problem under climate change impacts. So in Turkey, buildings are typically naturally ventilated through windows. These are occupant controlled, and actually the occupant control, let me say, of these windows is very unpredictable. But we followed some rules of thumb for occupant controls, and this constitutes the first scenario. And hybrid cooling was the second one, which combines natural ventilation plus air conditioning when natural ventilation falls short of cooling the spaces. The third scenario is probably the most wasteful, fully air conditioned with no natural ventilation. This is not the case in Turkey, but in some cases with some new high-rises, with some new condominiums, I think fully air conditioning is coming in the future. So this was one of our cooling scenarios. So we had to take into account the future weather conditions. We selected 260 as our study year. That means we are looking 40 years ahead from 2020. And we use existing methodology, existing tools. And the standard morphing methodology is the de facto method that takes a time series weather data, and it morphs or it shifts this data set based on different scenarios, climate change scenarios. So what we used was our RPC 8.5, which is the worst case scenario, business as usual scenario, with unchanged emissions and constantly increasing temperatures in the future. Alternatively, we could also analyze different pathways. 4.5 is another scenario that we analyzed, and Charlie is going to be discussing that in a few slides. But we created these weather sets for 4 different climates, for 4 different cities, for 2060. A number of performance metrics were used. The first one was energy use due to heating and cooling. We don't expect much change in operations or regarding lighting, so we only take into account heating and cooling, and the CO2 emissions due to heating and cooling. So we also, as part of this global warming potential, is calculated for natural gas boilers and air conditioners that run on grid electricity. They have different global warming potential, and this needs to be made part of our calculations. The second important set of metrics is regarding occupant thermal comfort. This is something that we expect to see major changes in if air conditioning is not installed in the future. So indoor overheating using fixed and adaptive overheating limits was separately discussed, was analyzed, and different adaptive control equations need to be used for day occupied spaces and night occupied spaces, and we calculate indoor overheating hours and indoor overheating degree. So I'm going to leave it to Cagla from here on. Cagla, you're on mute.
Okay. Hi, can you see my screen?
Yes, we can see the screen.
Yes.
Okay, great. So I will continue. Thank you, Ipek, very much. So I will briefly present our results, and I will not dwell into too much detail. So the first thing, when you check the impact of climate change on the built environment, is the projected climate. So here you see our projected climates, basic information on our projected climates for 4 cities that we have chosen. What you see is there are significant increases in summer temperatures and also in winter temperatures. The coastal cities and the inland cities, they are both prone to harmful effects of climate change. For Izmir, we see more than 4 Celsius of increase in summer months, whereas in Ankara, the difference will increase up to 5 Celsius in August. So actually, we see 4 or 5 degree increases in summer. This is actually very drastic for 2060. When we calculate the monthly cooling and monthly heating degree day values, actually this becomes more obvious. The cooling degree day values, even for Erzurum, rise more than 100%. And the heating degree day values decrease, but not as much. Sorry, my computer is a bit slow. Okay. So we calculated heating and cooling energy use and carbon dioxide emissions for 4 cities. What you see is the results for Izmir, Istanbul, Ankara, and Erzurum for a very typical TOKİ housing. You know, TOKİ houses actually, they host more than, I think, 5 million people in Turkey right now and increasing. So this actually can be a very generalized result considering how a large portion of the population lives in these houses or similar houses. So the first scenario is natural ventilation, that's denoted with A. And then we have the hybrid cooling, and then we have the fully air-conditioned scenario. On left, you see the energy uses, and on right, you see the global warming potentials. I want you to look at the scenario C, because that shows the more dramatic results in terms of energy use. In Izmir, we have around 48 kilowatt hour per meter square cooling right now, and this becomes 85 kilowatt hour per meter square in 2060 if basically we continue what we are doing. And the carbon dioxide emissions is actually very interesting because Turkey consumes significant amounts of lignite. Actually, we are the second after Germany, and Germany is actually reducing its lignite consumption. So what happens is we are actually burning a very dirty fuel. So our electricity is very dirty, unfortunately. And if you burn natural gas in a boiler, that's not that dirty actually. It's only 0.8 kilogram per kilowatt hour. So it's actually relatively clean compared to our electricity, which is higher than 0.58 kilogram carbon dioxide per kilowatt hour. So we are consuming a very dirty electricity when we increase air conditioning use. So instead of 26 kilogram of carbon dioxide, in 2060, we will produce around 46 kilogram carbon dioxide per square meter if we use fully air conditioned spaces. And let's check the heating. Heating in Izmir drops from 21 drops to 11. So it decreases, but not as much. And let's check the carbon dioxide emissions. It is right now 4 kilogram carbon dioxide per square meter. It will become 3 kilogram per square meter. So what you see is the change in the cooling cannot be compensated with the decrease in heating. Even in Erzurum, things don't look that good. Okay, heating will reduce, but we will have some air conditioning needs, which basically means our carbon dioxide emissions will remain roughly the same for Erzurum, which is the coldest city of all. And another thing I want to say is energy use is not everything, especially for residential houses. Okay, great, we're talking about air conditioning, that's right. But in Turkey, we rarely use air conditioners in our houses unless we live in Antalya or a very hot city, maybe in Izmir. But if in Ankara, for example, you're using air conditioning at residential houses is not that popular. So here you see 3 scenarios again: natural ventilation, hybrid cooling, and fully air conditioned scenarios. What you see on the x-axis is number of occupied hours, the percentage of number of occupied hours that you will be exposed to overheating, and on the y-axis you see overheating degree. So actually the results are very dramatic. In Izmir, these are adaptive temperature limits, by the way. So we assume that a person living in Izmir can adapt himself or herself to Izmir. A person in Erzurum can adapt to Erzurum. So these are adaptive temperature limits. What you see in Izmir, more than 80% of the occupied time, people will be exposed to more than 5 Celsius of overheating. This is a very dramatic case, which means air conditioning will become a must. And even for Erzurum, people will be prone to overheating, unfortunately. So they will have to switch to hybrid or full air conditioned scenarios. I also want to show you a slightly better version. This time I will focus on Istanbul because I didn't mention Istanbul in the previous ones. So what you see here is 2 scenarios. One is if we do nothing, if everything stays the same, business as usual, which is RCP 8.5. And the second scenario is RCP 4.5, which is if we do change things, and if we limit our carbon dioxide emissions. So your carbon dioxide emissions basically changes the way you project your climate. So we compare 2 scenarios: our worst case scenario, which is RCP 8.5, and in a way our best case scenario, which is 4.5. The reality will be something in between. Here you see the monthly temperatures for RCP 4.5 and RCP 8.5. There is a significant difference actually. So let's continue. So these are our monthly heating and cooling loads and also our global warming potentials. The dashed line, the coarse dashed line is the 2060 RCP 8.5, and the small dashed line is, the finer dashed line is RCP 4.5. What you see is let's check scenario C, which is the more dramatic one. So what you see is if you check global warming potentials in RCP 4.5 is around 6 or 7 in month July and August, and it will double if we do everything as usual and if we have an RCP 8.5 scenario. So your performance tomorrow depends on your performance today. So if we want to change things, we have to change them now so that we don't end up in RCP 8.5, but instead we end up in RCP 4.5. Of course, this is not the only important thing in residential buildings. Sorry if my son's voice is echoing in your in your heads because he's shouting right now. Sorry for that. So the more important thing is actually thermal comfort, because we're talking about residential units. When you talk about a residential unit, you have different zones. You have bathrooms, you have kitchens, you have living zones or sleeping zones or bedrooms. So for each of them, the way that people behave differs. So their thermal comfort, adaptive thermal comfort equations are different. So here you see the equations, graphs for Istanbul for bedrooms and living zones. They're actually temperature comfort limits are very different. On top, you see the overheating degrees for living zones, which are actually day occupied. And then on the bottom, you see the bedroom overheating degrees. What you see is bedrooms actually perform worse. Why? Because they have stricter comfort conditions. When you're sleeping, you cannot control your environment as much. So they have stricter adaptive limits. So even in a good scenario, we expect, especially in bedrooms in 4.5, we expect maybe 1 or 1.5, well, 1, at least in these simulations for this particular apartment, around 1 Celsius maximum overheating if we do keep things in a good way. But if we don't, the overheating in bedrooms will reach up to 4 Celsius 80% of the time, 80% of the occupied time. So this is a significant number. So to conclude, existing residential buildings are very critical for us because of their large share of carbon dioxide emissions, their vulnerability of their occupants to climate change, and because they have significant energy saving opportunities. The increase in temperatures due to climate change will shift the thermal balance of the buildings from heating to cooling. Problems regarding environmental impact and occupant discomfort and health are expected. Both passive and active building systems, as well as the effective integrated use of renewables, should be investigated to reduce climate change-induced vulnerabilities. I also want to continue that we actually study different typologies. For example, we study educational buildings, and you can check our publications actually. We also study offices, so you can check that publication, which is coming soon too. So we are not limiting ourselves to residential buildings because each building typology is unique. So you have to study, they have different occupancy profiles, and they have different loads, thermal loads. So you have to study each typology separately. Also, you have to study each climate differently. So please, if you have further questions on those, you can also ask us. And I think that is enough for today. Thank you very much for listening us.
Thank you, Ipek and Charlotte. That was another rich seam of information that I'm sure we can have great discussions about. I am, however, going to continue to move on to the next speaker now, and hope we can keep questions for the discussion because Alessia has to leave us at 12. So our next speaker is Alessia Buda from the Politecnico di Milano. Alessia, you have the screen.
Yeah.
If Charlotte, could you unshare so that Alessia can take over? Thank you.
Okay. Can you see the screen?
It's coming, I think. We're not getting the picture at the moment.
Oh. I've shared the screen, but maybe my computer is a little bit slow. Can you see it?
Yes.
Okay, perfect. Okay, so I think I can start. Good morning to everyone. I'm Alessia Buda. I'm an architect and I work for the Politecnico di Milano. I finished my PhD last year, working mainly on public buildings, public historic buildings in Mediterranean area. So today I will present some results of some case studies. Just a short note that with great pleasure with Valentina, we have just published a paper. So I hope that then you will find some interesting results there. So as you know, working on historic buildings is a not easy task. According to the need to reduce consumption and at the same time to give attention to the preservation needs. One of the main things is to combine the two goals in well-balanced strategies for maintaining the integrity, identity, and functional efficiency of this cultural asset. So my goal in the work done during the PhD thesis was to define a method, a multidisciplinary approach to support decision makers in this challenge. The main barriers we have to face during the planning are linked to these four topics. One is the legislation that, as you know, at all levels is pushing to reduce the requirements, the energy requirements for modern and existing buildings. That can have an impact also on historic buildings if applied. Another task of the legislation is that in almost all countries, we have exceptions for the monumental public historic asset. This exception is seen by heritage boards often as opting for doing nothing approach. So the question is how we can balance these two aspects, different totally aspects of the legislation, reducing at the same time doing nothing. Another task is the economics. We know that people prefer in general in public and private buildings to undertake the solutions that are sponsored by financial incentives. Of course, in this picture, you can see the main adopted solution in the historic buildings that come from before 1919 to the 50s. Another task is to balance the different aspects of the sustainability. So not only the energy aspect, but also the cultural, social, economic, and environmental, including the energy aspect. This means to find a synthesis between efficiency of use, operating costs, comfort, and conservation. And the last, but not less important task is the knowledge problem affecting the planning. As my colleagues said before, in Turkey, we have a lot of problems, mainly in the Mediterranean area. There is my main field in evaluating the characteristics, the thermal behavior of historic buildings, because we have difficulties in finding the elements, the correct characteristics of, for example, the inertial capacity of the walls, the time lag, the variability of internal loads. We have very complex material and constructive features. This problem can affect the planning because the simplification may underestimate the effects of intervention. When we use simulation tools, there is the topic of the workshop of today, we have to have clear in the mind that historic buildings need an in-depth analysis of these characteristics. In public buildings, another problem is linked to the number of actors involved. More actors are, more is the need for negotiation to define balanced solutions. So, going to the practical investigation that I've done during my PhD, I work on a huge project on 106 historic buildings in Sicily. Sicily is the south region of Italy. The work was to project the planning of energy retrofit in these very important buildings. My contribution was in the analysis of these buildings from the conservator point of view and give a support for the planning. Okay. So as I said, I've worked on Mediterranean climate because, as you can see, Italy, the west coast of Italy and the south part of Italy is considered Mediterranean climate according to the Köppen map. In Sicily, we have different climates, as you can see in the right picture. We have also more continental parts in the center of the region. So the number of case studies I've investigated is very large. So the first work I've done was the building categorization. I've decided to divide the buildings for their function because the different functions can also support in the definition of the goal for comfort. For improving the functionality of the building. Then I've worked mostly on 38 representative case studies. The variability support me to test the method, to validate the method on a large set. So as you can see, we have different typologies that are typical of Mediterranean climates. Construction characteristics, we have a range from 11th century to the 60s, dimension, and also, as I said, climate zone. So the method I've defined was the results of a study on existing guidelines and tools, mainly the new EN 16883 of the 2017. So the method was discussed with the Heritage Board of Sicily region, with buildings manager, and with the owner, there is the Sicily region. So the first part of the method was a preliminary analysis of the case studies. The second part was the data selection, so from the energy bills to the archival research. The third part was on-site survey that I've done also with interviews and monitoring. The fourth part was the data analysis, so combining data collection and on-site survey. The following step was the definition of targets according to the use of the building mainly, and to the results of the data analysis. So then the measure selection, and finally the assessment of measures according to a multi-criteria system. The first part of data analysis support me to define, for example, anomalies on the large scale. The step after the on-site survey, as I said, was the combination on monitoring and also interviews, support me to see some of the main problems in whole buildings. we can synthesize them in 4 points. The first is the lack of maintenance and monitoring. So, for example, as you can see in the pictures, we have unhealthy conditions, not only for the users, but also for the conservation of the artworks in the museums, for example. The second point was uneven distribution of the technical installations as temporary installations, not as a result of an integrated project. That can affect also the aesthetic integrity of the building. The third point was the human behavior impact. Most of the time I've seen, for example, open windows while the system was on. I've calculated 8% of shift of predicted consumptions in the buildings. And the fourth and last point was the lack of care for preserving the building. This means that some actions were damaging the building. For example, the use of the position of the armchair in front of ventilation channels and so on. So according to the opinion of the Heritage Board and the building manager, we have defined for a different type of building with different functions, general project targets. This is an example in the museum, microclimate indoor control for artworks in the office, workers' comfort, and so on. So we have also, in general, for the 106 case studies defined, solutions suitable for the single case according to the results of the survey. This is an example, a comparison between the standard solutions that we normally see in the in project of retrofit on modern buildings and the alternative solutions we have proposed. But I want to show you one example. There is a museum. Is a really important museum in Palermo, Palazzo Batellis, which is in Mediterranean climates. The first actions was the data analysis of existing consumptions. So respect to the average consumptions of the all museums we have in our set, the Palazzo Batellis consumptions were not that higher, only in the lighting parts were higher. So thank you too for the catalogers that were already existing in the exhibition rooms from years, and with the combination of instant relative humidity and temperature meters, I've defined 35 thermal zones. So I've worked mainly in Energy Plus, but for other simulations, I've used also other softwares. The on-site survey reveals mainly moisture problems at the ground floor and some infiltration problems also from terrace. Technical installations were placed not in all the exhibition rooms. So we have also variable range of temperature, relative humidity from one space to another. The lighting was not positioned according to the visitor point of view. So as you can see in the right picture, there's lighting discomfort. So for this example, as for the others, we have proposed a selection of measures, and for all the measures, we have also then combined in scenarios the different options. So I've run 80 simulations for that. As you can see, the measures were not only on the envelope, window, floor, roof, and wall, but also on the technical installations, and also on the management. That was one of the weak points in all the buildings. So for the assessment, the method developed during the PhD was to combine qualitative and quantitative indicators or targets. As you can see, all the aspects on the that I've on which I worked are those that I mentioned before in the sustainability pillars. So heritage, economy, environments, comfort, and I have added also management. For the qualitative aspects, I've defined the PhD some systems to evaluate them, has some questions that the designer has to answer. Is not an easy task to evaluate something that is qualitative, but trying to make the questions more explicative as possible, this can support to avoid some risks for the building. The same, for example, for technical compatibility, I've combined both quantitative and qualitative evaluations. So, for example, in this building, for the definition of the solutions on the window, I've tried to evaluate according to a multi-criteria matrix the three options. As you can see, I've underlined some negative or acceptable with notes elements. This type of matrix is a support to have a discussions with the stakeholders and give really concrete elements to discuss. The main problem in the negotiation with public administrations is to have elements, and thank you to the simulation tools, this can be our results. The same was done, of course, not only for the single measures, as I said, but also for scenarios. And at the end, we have defined the best alternative solutions to the most common scenario we think at the beginning. So as you can see, with similar investments, we have calibrated evaluation of measures, we have more cost savings evaluated thanks to the simulation tool. So the same was done also for other examples, this is, for example, one modern building that is considered historic, as was constructed by a very important architect in Italy. So the envelope is totally different from the 15th century building that we have seen before, but we have common problems in the building conditions. For example, we have also here some water infiltration, some problems with skylights that were broken. So we have done the same typology we have followed the same methods. As you can see, solutions for all aspects, both envelope and technical installations. And thank you to the matrix, we have compared the different solutions. Then we have combined them in the best scenarios to select the best one. So the main results of this analysis of this investigation on case studies was that we have seen that also the same solutions in different climate zones may have different influence. We have seen that in in a hottest climate, for example, the insulation may be counterproductive. We usually think that the most standard solution and interventions, like, for example, insulation, are the best for reducing consumptions, but in a Mediterranean climate, in hot climate, we have to think differently because the main problem is in the cooling. One of the main results was done, for example, in the roof with the use of reflective thermal coating. In the window, the use of shading was one of the main elements for reducing the overheating inside the building. Respect to modern architecture, it was major difficult to evaluate the envelope characteristics, of course, in the simulation tools, and we have lower flexibility in the choice of interventions. But at the end, solutions very calibrated on the single case studies give huge results in terms of energy consumption, but also of comfort conditions in the simulation. So what I got from this experience is that, as I said, decision making is a negotiation task that is variable case by case. We have to give priority to the building knowledge because this gives the rules of the project. In general, it is necessary to change the approach. The attempt was to combine the different aspects of in the planning, the different aspects of sustainability, so culture, economy, society, and environment. And I can say that after discussing a lot in the interviews, in the meeting with public administrations, only having a multi-criteria approach can support to define very balanced solutions. Last point is that it's necessary in general to invest more energies on the training. As I said, one of the main problems in the buildings was the lack of recognition for the importance of historic buildings. When I was in the buildings during the on-site survey, I talk a lot with the managers, and they often said, yes, it's sure. I can close the window when the system is on. Oh, I forgot it. It's something that seems stupid, but many times has to be spent in the training in public buildings. So in the future, I'm starting to work in the postdoc on the guide for stakeholders. Thank you to this experience in this huge number of case studies. And I hope to present to you in the next workshop. So thank you for the attention. And I think that's, if someone has questions.
Alessia, thank you very much. Another presentation full of information that I'm sure we can chew over for a very long time. I understood that you might have to leave right away. Is that still? So yes. What I suggest is that if people have questions for you, we ask them to put them in the chat and we will send them on to you. We'll email them if that's all right.
Yes. Okay.
Great. Okay, we'll do it that way because we're also quite well behind already. So in that case, I'll thank you very much for that. I'll move on now to Valentina, our colleague from UCL, Valentina Marincioni, who's going to slightly change the theme now for our final presentation and talk about hygrothermal simulation in this context. So Valentina, over to you.
Thank you, Peter. Can you see my screen?
Yes.
Okay, great. Yeah, so this is going to be slightly different, so not focused on energy, but as many of the speakers already mentioned, energy has to be integrated with other disciplines. And there are other types of simulations that can help with a quantitative or a qualitative assessment of other risks associated with the sustainable retrofit of traditional buildings. So I'm going to just give an overview of some of the projects we've been working on in UCL. Mainly exploring the use of hygrothermal simulations to support decision-making with a specific example of the sustainable retrofit of walls in traditional buildings. So as this was already mentioned, what we need in a sustainable retrofit, we need an integrated approach and an integration among disciplines. So from my side, as you will see later, I work on the technical compatibility and so building and health. So that's the green part that you see in this chart. So there are, of course, other very important elements, but in this presentation, just focusing on that. Something I want to mention is that this has to be considered within a whole building approach. So thinking of interconnecting fabric, services, and people within the context of the building under consideration. And also considering a joined-up approach. So not just the assessment and design, which is what we are focusing on in these projects, but also the installation and use. So there has been a focus, at least in the UK, there has been a focus on low carbon or low energy retrofit in the last few years. However, we found that there are some unintended consequences associated with that. And these are just some examples from the UK. A couple are some of my case studies, where you can see some frost damage, you can see some mold growth at junctions. And the third is from one of the cases, the large retrofit schemes happening that were funded in the UK, and they led to mold growth. So I suggest looking at that for more. So that was just to show why we need to extend our horizons and look at health and durability as well as energy. But of course, there are many more elements for an integrated approach. So it's not just energy and comfort, also preservation of heritage values, health, indoor environmental quality, and durability, which is what I'm going to focus on. And those are particularly related to moisture management. Then we have resources, economic viability, cost, and building use. So there are many of these buildings have a change of use. So as Alessia was saying before, the users have an impact on the building. And of course, we don't design for buildings, we design for users, for people to use the building. So we have to consider those. That's at the heart of our work. So these are going to be 3 examples on how we can use hygrothermal simulations to support decision-making with a particular view on walls. Walls, why walls? Walls are a bit tricky for heritage purposes, and in several countries, wall insulation is the last to be done, or it's also not suggested and recommended as a retrofit measure. And that's because there are several technical issues associated with the implementation of wall insulation. Particularly for heritage buildings, one of the few options is to install internal wall insulation, because that can help retaining the facade and retaining the heritage values associated with the facade. However, there are several technical issues. Adding internal insulation could damage the existing wall because it changes the wall's moisture balance. And the different systems will lead to different risks. So it's important to compare the results associated with different systems. So overall, moisture issues associated with internal insulation include mold growth at the interface, include mold growth at the surface if surfaces are not properly insulated. So for example, at junctions and in hard to reach areas, and also include frost damage and salt efflorescence on the outside. So there are several issues associated with that. The first example I want to show is how we use hygrothermal simulations and the probabilistic approach and sensitivity analysis to understand the factors affecting mold growth risk at the interface between the existing wall and internal wall insulation. So this could be useful if we want to understand what are the parameters that we need to address before deciding to go for internal wall insulation. If we look at the sensitivity analysis, the result here, the first parameter affecting mold growth at the interface is orientation. And this is something that, of course, we cannot change with an existing building, but that suggests that we might need to have different strategies at different orientations. The second part is the rain exposure coefficient. So if the building is fully exposed to the weather, to the elements, or if the building is in an urban area, that will have an impact. And then there are several parameters which are important for the insulation. So there are some material properties of insulation which make a difference in terms of moisture risk. So that suggests that we would have to look for systems with certain saturation moisture content, or certain liquid water conductivity, or certain thickness, or certain vapor diffusion resistance. So based on these 4 parameters for the insulation, we can decide the insulation system that is more beneficial or that carries lower risk from a moisture perspective. So of course, this is an example that was for West Wales, which is a temperate maritime climate in the UK, very wet, very highly exposed to wind-driven rain. So we are talking about quite extreme conditions. But the method can be applied through for other cases. The second example that I wanted to share is using simulations to allow for a fast probabilistic moisture risk assessment. So we used a similar framework to the sensitivity analysis, but we extended it to create predictive models. And these predictive models allow us to quickly assess whether the building in the location of our choice, whether the building is at high or low risk and with that specific insulation system. So we predict the mold index, and we compare the mold index to failure criteria which are in the literature. So if you see there, you have a yellow line and a red line, and these are the 2 criteria, the 2 thresholds. One is a mid threshold, and the red one is a no-go threshold. And so basically that shows that in areas in West Wales, this is for West Wales, and this was an internal insulated 9-inch solid brick wall. So it's 225 millimeters thick. So fairly exposed area, but in case of full exposure to the elements, we could only insulate on the northeast facade. So that would be the result. So low risk for the northeast, but very high risk for the southwest. However, if the building was in areas that are less exposed to wind-driven rain or had further protections like overhangs or renders, lime renders, therefore the risk would have been lower to the southwest. So again, that element of orientation is quite important. So we might need to consider not just the main facade or orientation, but also the exposure to the element. And then the last example that I'm just going to go a bit deeper in the example is assessing the climate resilience of internal insulated solid walls. As we've seen before, there are the future climate is likely to change drastically. So therefore, we shouldn't design for today, but we should design for as long as we can. Especially, this is especially critical in traditional and historic buildings because we want to maintain the technical compatibility and we want to extend the durability of a building by insulating and by a renovation project. So the analysis we did considered the current scenario and an extreme, so a near extreme reference year. So a current scenario with 90th percentile rain. And then we consider projections in the near future to 2040, and in the far future to 2080. And we consider the same business as usual scenario that Ipek was mentioning before. So I'm going to show a quick analysis of the climate, of the wind, river, rain in particular. But before that, I'm just going to show you the other inputs. So we've considered two U-value targets. So one target that is the building regulation target, 0.35 watt per meter square Kelvin, and the other target is a more relaxed U-value, 0.6. And we consider several failure criteria. Today, I'm just going to show you moisture accumulation, which is the first one, but we've also considered mold growth and frost damage. For this comparative analysis, we consider three of the main systems for internal wall insulation. One is phenolic foam, so closed cell form insulation. Second is calcium silicate, so it's a capillary active system which is able to absorb water. And the last one is wood fiber, which is another capillary active system that is less able to absorb water, but better in with higher ability to absorb vapor, so water in vapor state. Anyway, three systems that could be used for this kind of example. So the first analysis that we did, we looked at the climate scenario using the Met Office is releasing in the UK, is releasing projections. So we've post-processed those projections that are available for London. And we've looked at the current scenario. So currently, if we consider in the year with the 90th percentile of rain, so a quite extreme year within the last 10 years, these are the wetting and drying periods. So wetting considering October to March and drying April to September. And these are the wind-driven rain, the overall wind-driven rain considered for both periods. So currently, this is the level of wind-driven rain in the wetting and drying period. A similar scenario would be seen in the near future. So very similar wetting and drying wind-driven rain. But in the far future, we are seeing a very different picture. So much higher wetting and much lower drying. So much higher, wind-driven rain in wetting and much lower wind-driven rain in drying. So much more, the seasons will be different, much more different compared to now in terms of wind-driven rain patterns. And we've not only looked at the 90th percentile, which is an extreme case, but also we looked at the 50th percentile because we wanted to see really whether that was a case only for the extreme scenario or also for an average scenario. And that was the case for both. So definitely we need to think how to design and renovate buildings for the future. So the results of the three cases, they show that under the current climate, current U-value standards have medium to low moisture risk for the current climate. However, when we look at the future climate, the risk is much higher. So therefore, risk is going to increase with the future climate projections. Among the three systems, capillary active insulation performed best under both current and future scenarios. And on the other hand, closed cell foam performs worse than the other two and much worse in the 2080 scenario. So you can see low drying for the red, which is the phenolic foam. So it showed very limited drying. So that's how, for example, we can decide for what system to use at the end. And something else that I want to mention is that additional interventions will be needed to reduce high risk of future moisture load in this case, because anyway, the three systems are quite high, show quite high relative humidity. So it's important not to consider only one system, but again, the system as part of a whole renovation process where other elements are included, like deeper overhangs and so on, to improve the moisture balance. And then also, last but not least, we compared the two U values, so a high and a low U value, and we concluded that thinner insulation systems perform better in all systems, and they should be allowed for solid wall retrofit, in particular for buildings of high value that need to be insulated. So overall, hygrothermal simulation can help, first, understanding the factor affecting moisture balance in solid wall retrofit. Second, performing a fast probabilistic moisture risk assessment. And that's in particular if we look at large scale strategies for maybe a large number of buildings or a district or a specific area. And then we can use hygrothermal simulations to assess the climate resilience of potential measures for solid wall retrofit. And last but not least, again, we can use hygrothermal simulation to select retrofit measures and strategy. However, we need to remember that this must be integrated with other disciplines in a whole building approach. And that's why this type of simulation is well suited for the retrofit strategy, because it can give further understanding for the final negotiation process. Thank you.
Thank you very much, Valentina. I think you've demonstrated pretty well how important hygrothermal simulation is to this process. Lots and lots of discussion of energy simulation this morning, but bringing the hygrothermal element into it is clearly a very important factor. I did have one question for you myself, which is you talked about thinner insulation being better, but did you mean worse U values, higher U values are better than lower U values?
Yes, yes.
It doesn't
so,
really mean the thickness of the material, it's what performance you're trying to do.
Yes, so that was the way we simulated the thickness was associated with the U value. So we simulated thicknesses that led to a specific U value. So therefore, a lower U value can help mitigating moisture risk. Yes. And of course, if we think of if we start looking at the other aspects, thinner insulation is also beneficial from other perspectives, like the space, the proportions of the building. So therefore, it would be also beneficial from other qualitative aspects, which are as important or more.
Thank you. Well, we're very late, but nevertheless, all of the panelists except Zeynep and Alessia are still with us. So if there are participants who want to ask questions, verbal questions, we're happy to take a few for those who are happy to stay on. Or again, if you want to put questions in the chat, we will try to answer them. If you want to ask, then please do just open up your microphone and camera and ask the question. I'm not getting any. Or you can put the questions in the chat. I do have a question that's from Bilge. It's in the questions already. Yasmin's attempted to answer it, but the question says, is there any integrated study about structural damage, such as cracks and movement with temperature and moisture in historical buildings? He's studying on some sensors. He's studying on some sensors to measure crack movement, and he's wondering about using these sensors for some case studies. I don't know whether anybody wants to pick that one up. Do you know of integrated studies, Valentina? No. We may not have an answer for you, I'm afraid, on that one. That's all I've got in the questions box at the moment. Okay. I don't see any hands up. Let me just check. No, I think perhaps we've overwhelmed everybody with the rich technical content of all the presentations. So maybe we will leave it at that, but we will try to get questions to people if any want to be submitted. I want to say thank you very much, first of all, to all our speakers. It's been quite a challenge to get you all into the time available, but I've been very struck by how much common ground there is in the way people are approaching these problems, and how much information there is out there from multiple sources about how we can deal with this issue. And whereas I thought before that our PROTECT project was sort of on its own doing things, I now realize that it's alongside a huge amount of other work that we need to assimilate. So that's really encouraging. Also wanted to thank the sponsors of our program today, named at the beginning. We couldn't be doing this work without, and I hope that everybody's enjoyed. Thank all the participants as well. I hope you've all enjoyed listening to our speakers today. I certainly have. So I think at that point, one more question's popped up. No, it's just thanks. Okay. So at that point, I think we'll say we should close the meeting and look forward to our next workshop at some point in the near future. So thank you very much and goodbye to everyone.
Thank you.
Bye.
Bye.
Thank you. Goodbye.
I'm going to leave.